positive charge is moving to the right and experiences an upward magnetic force, as is just shown below, in which direction must the magnetic field have a component. So they give us the direction of the velocity, and they give us the direction of the force. So now remember that when you apply the right-hand rule, you must put your 4 fingers in the direction of the velocity. And when you fold the fingers, those fingers now should be pointing in the direction of the magnetic field. And then the thumb would be pointing in the direction of the force. So the only way to know, the only possible direction that this magnetic field can be acting, so that happens, you know, that your 4 fingers are pointing to the right, and later when you fold the fingers, you know, they point in the direction of the magnetic field, but the thumb points in the direction of the force, is if the magnetic field points toward the paper. That means when the magnetic field enters into the plane of the paper, right? So now just do the test. Put your 4 fingers in the direction of V, so pointing to the right. You now fold your fingers toward the plane of the computer, the screen of the computer or the paper, right? And then you will see how your thumb is pointing forward, right? So in this case, the right answer would be into the page. So the right answer here is into the page. Next question, they say 2 long parallel wires are placed side by side on a horizontal table. If the wires carry current in opposite direction, then now they give us several options there. So they say both wires are lifted, slided. One wire is lifted while the other wire is forced downward against the table surface. The wires pull toward each other. The wires push away from each other. So let's analyze together, you know, what happens when you have, in this case, wires, and they have currents in opposite directions. So this is the wire 1. So there will be a current here that we're going to call current I1. And then there will be here the second wire. Now, in the case of the second wire, the current is pointing in the opposite direction. So this is the current I2. Now, you know that now to find the direction of the magnetic field, right, which is going to be circular around the wire, you should put your thumb in the direction of the current, you know, and then when you fold the 4 fingers, it gives you the direction of the magnetic field. So if you find the magnetic field due to the current I1, above the wire I1, the magnetic field due to I1 would be leaving the plane. So this is P1, right? And below the wire 1, the magnetic field would be entering into the plane, right? All below, it will be entering into the plane. So now, when you want to find the force due to V1 acting on wire 2, right, you would put the fingers in the direction of I2. You will turn the fingers into the direction of the magnetic field, right, and the thumb is going to give you the direction of the force. So if you put your 4 fingers now to the left in the direction of I2, and you turn your fingers toward the plane of the computer, or the screen of the computer, the plane of the paper, you will see how your thumb points down, right? So the force acting, on this wire 2 would be a force acting downward, pointing downward. So this would be the force on wire 2 due to 1. Now, let's do the same for the other wire. Now, wire 2, when you analyze, you will see how if you put your thumb in the direction of the current, the magnetic field will enter above and will be leaving the plane below wire 2. So the magnetic field due to 2 will be like this. And then above here, it will enter into the plane. So now, if you want to find, of course, right, what is the direction of the force on the wire 1, you will put your 4 fingers in the direction of the current 1, you will fold the fingers toward the magnetic field, and you will see your thumb pointing up. So the force on 1 due to 2 would be like this. So now it's clear, right, that as these 2 wires are resting on a surface, are just placed side by side on a horizontal table, they are just, the force just try to push them away from each other. So the right answer in this case should be answer D, that is that the force pushed them away from each other, right? So remember, these 2 wires are on the plane, so they are both resting on the plane of a table. They are resting on the table. So now what the force is doing is just pushing them away, one from the other. Let's see the next case. So they say now a vertical wire carries a current straight up in a region where the magnetic field vector points toward the north. So what is the direction of the magnetic force of this wire, right? So this one is a little bit more difficult to see because here we have, a 3-dimensional problem, right? So let's say that the north is just entering into the plane of the screen, the plane of the computer. The south is leaving that plane, then the west is to the left, the east is to the right, and then of course we have up and down, right? So basically here we have a wire here, and it carries a current straight up. It carries a current straight up. So the current here is just like this, and it's just up. Now they say that the magnetic field vector points toward the north. I said that the north would be entering into the plane of the screen. So the magnetic field vector enters into the plane of the screen, which is north. If now you put your 4 fingers in the direction of the current and fold your fingers toward the direction of the magnetic field, you will see your thumb pointing to the left, and the left is the west, right? So in this case, you will see how, the force here points, the magnetic force points in this direction, and the direction is just the west. So the right answer here would be toward the west. Question 21 is just similar to question 20, sorry, to question 19, but in this case, the currents are in the same direction. So let's analyze then this question 21. We have the two currents, so the two wires with currents in the same direction. So this is the wire 1, this is wire 2. They are placed side by side on the horizontal table. If the wires carry current in the same direction, so this would be my current I1. And let's say that this one is going to be my current I sub 2. Now, when we analyze the magnetic field due to I1, you see the right-hand rule. You put your thumb in the direction of the current. You see how above the wire 1, the magnetic field is leaving the plane. And below the wire 1, the magnetic field is entering into the plane. The magnetic field due to the current I1. So this is the magnetic field B1. Right? So now, if you just put your fingers in the direction of the current I sub 2, and now you fold your fingers in the direction of B sub 1, you will see how your thumb points forward. This will be the force on wire 2 due to wire 1, due to the current I1, or due to the magnetic field, due to current I1. Now we can do the same for the magnetic field due to I sub 2. So when you just apply the right-hand rule to I sub 2, you put your thumb in the direction of I sub 2, and you would now wrap your fingers in, all around the wire 2. You will see how the magnetic field is leaving the plane above the wire 2 and is entering into the plane below the wire 2. So if now you put your 4 fingers now you put your 4 fingers in the direction of the current 1, and you want to fold the fingers in the direction of B sub 2, you will see how your it's difficult to put the hand in this position. So you will see how the force will be pointing downward in this case. So this will be the force of 1 due to 2. So you can see here, in this case, the wires pull toward each other. So basically, the force that is acting on these wires is just pulling the wires, toward each other. Okay? And that's basically what happens when the currents are flowing in the same direction. The wires are going to move toward each other. When the currents are just acting in opposite direction, the wires are going to move away from each other. But what is always good to just demonstrate it, to make analysis to make sure that we understand. Now let's see, there's a sign number 22. They say when 2 parallel wires carry unequal currents, the magnitude of the magnetic force that one wire exerts on the others is F. Now, if the current in both wires is now double, what is the magnitude of the force on the new wire, right? So we know that there are 2 long parallel wires. So usually we have the force per unit of length, and this force per unit of length is equal to mu sub 0, I sub 1, I sub 2, over 2 pi r. So you have two long parallel wires, you don't know the length, that's why we usually use force per unit of length, so F over L. You know, then you have this force per unit of length depends on the current of both, the flow to both wires and also in the distance between the wires. So R is the distance from wire to wire, right? Now, if they say if the current in both is now double, what is the magnitude of the new magnetic force on each wire? So if now we have that I1 prime is 2 times I sub 1, and that I2 prime is 2 times I sub 2, if we want to find, the force per unit of length prime is mu sub 0 I1 prime I2 prime over 2 pi r. So it would be mu sub 0 2I sub 1 times 2I sub 2 over 2 pi r. So this would be 4, 2 times 2, 4, mu sub 0, I sub 1, I sub 2 over 2 pi r. So it would be basically 4 times F over L. So that means that now my new force per unit of length, F over L prime, would be 4 times the initial force per unit of length, right? So basically what you say, okay, the new I1 value would be twice the initial I1. And the new I2 value, this is what I call I2 prime, is going to be 2 times I sub 2. And when I plug it in now, to find the new, so the prime, F over L, force per unit of length, we get that this is mu sub 0 times 2I1 times 2I sub 2 over 2 pi r, which is going to be 4 times mu sub 0 I sub 1 I sub 2 over 2 pi r, which is then 4 times, the initial force per unit of length. So in this case, the right answer is 4 times F. So basically, we are multiplying by 4 the magnitude of the force. I use force per unit of length. You can also have the length, multiplying there. It doesn't matter, right? So it really doesn't change anything because L doesn't change. So you are just two long wires. Now look at the next one. They say two long parallel wires carry currents of different magnitudes. If the current in one of the wires is double and the current in the other wire is half, then what happens to the magnitude of the magnetic force? Each wire hertz on the other. So we have now same case. So again, two long wires. And now what happens is that we're going to double the current in one of them, but we're going to reduce to 1/2 the current in the other. So if now I sub 1 prime is 2 I sub 1, but I sub 2 prime is 1 over 2 I sub 2. Now when you want to find F over L prime, it would be mu sub 0, 2 I sub 1, 1 over 2 I sub 2 over 2 pi r. And then what happens here? Well, these 2 and this 1 over 2, they just cancel to each other, right? Because 2 times 1 over 2 would be 1. So basically, you will get the same mu sub 0 I1 I2 over 2 pi r, right? So it's the same force per unit of length. So basically, the force didn't change, right? So we get the same, it stayed the same. Let's see the next one. They say, let's see. Yeah, let's see the next one. They say two long parallel wires carry current of different magnitudes. The amount of current in one of the wires is double. What happens to the magnitude of the force that each wire inherits on the other? So, well, this is evident. You double one of the currents, the rest of the coefficients stay, the rest of the values stay the same. We double the magnitude of the force, right? So we can demonstrate it. It's just basically like say, oh, F over L, which is mu sub 0 I1, I2 over 2 pi r. Now I have that I1 prime is 2I1 and that's it. The rest is the same. So when I find F over L prime, you know, it would be mu sub 0 times I1 prime, which is 2 times I sub 1 times I sub 2 over 2 pi r. So this would be 2 mu sub 0 I sub 1 I sub 2 over 2 pi r, which is 2 times F over L. So basically, you know, over F over L prime is twice F over L. So we double, we increase by a factor of 2 the magnitude of the force. Now look at the next one. They say the magnetic field at the distance of 2 centimeters from a long straight current carrying wire is 4 micro Tesla. So what is the magnetic field at the distance of 1 centimeter from this wire? So let's see what is the equation of the magnetic field surrounding a current carrying wire. So the magnetic field surrounding a current carrying wire will be B equals mu sub 0 I over 2 pi r. Now, when we have that we reduce r from 2 centimeters to 1 centimeter, basically what we say is that r prime is 1 over 2 of r, right? Why? Because r was initially 2 centimeters and it was reduced. So we call this r prime. The conditions, 1 centimeter, right? So we now can just replace r prime by 1 over 2r, and we get that b is equals, mu sub 0 I over 2 pi r. This is b prime, and then r would be 1 over 2r. R prime would be r 1 over 2. So we get a b prime. The magnetic field under the conditions is flipping this 1 over 2 is 2 times mu sub 0 I over 2 pi r. This mu sub 0 I over 2 pi r, it was 4 micro Tesla. So all this expression, was equal to 4 micro Teslas. And then 2 times 4 micro Tesla will give you 8 micro Tesla. Right? So when you reduce the distance to 1/2 or by a factor of 1 over 2, then now you double the magnitude of the magnetic field. Right? So now the new magnetic field is 2 times the original magnetic field at 2 centimeters. So the right answer here is 8 microteslas. Remember, that here they give you the original value of the magnetic field, and they said here 4 microtesla. So this 4 microtesla is the value of this field. Okay? So now, when you say, oh, R prime is 1 over 2R, and I just find B prime, the new magnetic field, and then I replace instead of R by 1 over 2R by R prime, then I just flip this 1 over 2, it turns into 2, and 2 times 4 would be 8 microteslas. Now look at these other problems. They say that a bar magnet is oriented above a copper ring, as is just shown below. If the magnet is pulled forward, what is the direction of the current induced in the ring as viewed from above? As is viewed from above. So what happens here? We have our magnet. This is north and south, right? Let me see if I can just get what happens here. Well, what happens here? Now, the magnetic field here will be like this, right? So it's entering the South Pole and it's leaving the North Pole, right? This is how the magnetic field lines. Now, when you are moving, this magnet forward, the magnetic field in this loop, in this copper ring, is decreasing, right? So there should be now an increase in the magnetic field to counteract that decrease. So the current that would be induced is going to try to counteract, that decrease in magnetic field, right? So that means that now here we should have a magnetic field that would be in this same direction to counteract the decrease. This is the magnetic field inducing. Now, the only way that this magnetic field is induced in that direction, so in the inner part of the ring, it's just pointing up. If your 4 fingers try to wrap the ring, and you will see how the current will be flowing in this direction. In the front of the ring, the part of the ring that is in front of you, it will be pointing to the right. So that means that the current here would be just in this direction. And well, if you analyze the current here, it would be like this here, right? Now, if you look at this from above, so the position is important. If now I look at the ring from above, I will see the current just flowing like this. And this is counterclockwise. So this current would be counterclockwise. So if you're moving the magnet away from, the ring, the magnetic field, the magnetic flux across the surface of the ring, right, or across the area of the ring is decreasing. So the current that is going to be induced, we try to counteract that decrease just inducing a field, that is also in that same direction to counteract the decrease, And then if it's in that same direction, it's also in the direction that I represent, that is like over, right? In the inner part of the ring. And then if you, the only way that you apply the right-hand rule, the only way that you can just get that direction of the magnetic field if it's the current flows counterclockwise from above. Now look at the next one. It's very similar, but they ask you to analyze this from below, to see this from below. So they say if our magnet is oriented above a covered ring, if the magnet is kept fixed while the ring is dropped, right? So it doesn't matter if it's the magnet who is moving or if it's the ring who is moving, right? So at the end, there would be a change in magnetic flux, which is what matters. So the magnetic flux across the ring is going to decrease, right? So if the magnet is kept fixed while the ring is dropping, what is the direction of the current induced in the ring as viewed from below the ring? So we have the same thing basically, right? So we have basically the same thing. Because now what is going on is that the magnet is staying in the same place. Right? But the ring is being dropped. So anyway, there is a decrease in the magnetic field across the section of the ring. So the ring, there will be an induction of current in the ring that will try to counteract that effect. So as there was a decrease, the magnetic field that needs to induce it needs to be in the same direction. And the magnetic field due to the magnet. The only way this can happen is, as we have analyzed before, if the current now flows like this. Now, if you look from below the ring, and that's why it's important the reference, if now you look from below the ring, what do you see from below the ring? You will see a current that just goes clockwise. So this first case here was from above. And now here is from below the ring. So you can see the current now is clockwise. So you have to try to see this in 3 dimensions. So you have to stand below the ring and look up. Look it up, and then you will see how this front part of the ring is just this part of the ring, that you see here above, right? And then you will see the current just flowing like that in this direction, clockwise. It's difficult, to hide this in 3 dimensions, but we can always, try to. Let's see then the next problem. Any questions so far, John? No? Victoria, no questions? Okay. Look at this other. This one is also very interesting. They say the wire in the figure carries a current I that is increasing with time. So you have that the current I is a function of the time. You have a current I of t, a current that changes with the time, you know. So we have the current pointing to the right. As this is a current that is changing with the time, we have a change in magnetic field. So we have a change in magnetic flux through the rings. So we have three rings, or three loops. So they say the wire in the figure carries a current I that is increasing with time at a constant rate. The wire and the three loops, or the three rings, are all in the same plane, right? What is true about the currents induced in each of the three loops given below? We have to analyze, what happens here. When you analyze, you see that for the direction of the current to the right, okay, you will have the magnetic field above the wire points outward, and below the wire points inward. Right? Now, what happens? With the ring that is split in two equal parts by the wire, you have the same number of magnetic field lines leaving the plane that magnetic field lines entering into the plane. So the magnetic flux above cancels the magnetic flux below. So basically here, there is no current induced. The current for this one will be zero. There will not be current induced in this one because the magnetic field above counteract the magnetic field below. The magnetic flux above is counteracting, the magnetic flux below. One change in magnetic flux cancels the other change in magnetic flux, right? Because it's split evenly by the wire. Now here, we have an increasing current, okay? Now above, we know that the magnetic field is like this. And it's increasing. So the wire needs to generate, now a current, or a current will be induced in the ring above, that will counteract this. That will counteract this increase. The way to counteract that increase is to induce a current that just is opposite. The magnetic field will be opposite, right? So the magnetic field due to the new current that would be induced there in the inner part of the ring, would be opposite, would be entering into the plane, right? Because the magnetic field due to the straight wire is leaving the plane, right? So the only way that is going to happen, right, is if the current that we have here is clockwise. So the current being induced here is clockwise, right? So we remember, in the inner part of the ring, it has to enter into the plane. So the current will go like this in the ring. Now, what happens below? Below, we have, that the magnetic field due to the current I is like this. So in the inner part of the ring, of the loop, you have a magnetic field that enters into the plane, but it's increasing. So the current that will be induced needs to counteract that. So it needs to be opposite in direction to that field. So the new field, will be like this, inside here. So the only way that that field will be leaving the plane inside the ring, if it's when you wrap your fingers around the loop if the current points, counterclockwise, just like this. So what happens? Loop A has a clockwise current. Loop B has no induced current. And loop C, which is this one, have a counterclockwise current. So the right answer here is the answer D. Now, words matter. Here they said that we had a current I that is increasing with time. Here they say that there is an steric current I. So in this case, we have no change in the magnetic flux. So no current is induced in any loop because we have no change in magnetic flux, right? Now, the analysis in number 30 is basically the same. Let's go now over some problems. Number 32, for example. They say an electron moves with a speed of 5 times 10 to the 4 meters per second, perpendicular to a uniform magnetic field of magnitude 0.20 Tesla. What is the magnitude of the magnetic force on the electron? So remember, and of course, then you will have your notes open, right? So remember the formula that we have for an electron that is moving in a uniform magnetic field and is moving perpendicular. So the equation to calculate the force is force equals, the charge of the electrons times the speed of the electron or velocity of the electron times the intensity of the field times the sine of theta. So theta here, is the angle second. Yeah, theta is the angle between the velocity vector and the magnetic field vector. So since they say that the electron move with a speed that is perpendicular to the uniform magnetic field, then when they say perpendicular, it's because theta is 90 degrees. Now, we know the charge of the electron, that is 1.60 times 10 to the negative 19 coulombs. We know the speed, that is 5.0 times 10 to the 4 meters per second. We know the intensity of the field, that is 0.20 Teslas. And then sine of 90 degrees. The sine of 90 degrees, the sine function, the sine function is a function like this. So here at 90 degrees, it takes a value of 1. So sine of 90 degree is going to be 1. So you will get that the force is going to be, so you calculate 1.60 times 5 times 0.20 and then 10 to the negative 19 times 10 to the 40 is 10 to the negative 15 later. You will get that this is 1.6 times 10 to the negative 15 newtons. So the magnitude of the force in this case would be 1.6 times 10 to the negative 15 newtons. Now, what is important to understand here when they say perpendicular, when they say that the speed is perpendicular to the uniform magnetic field, what they say is, okay, the angle theta between the speed and the magnetic field is 90 degrees, and the sine of 90 degrees is 1. Okay, so that is important. Now look at the next. They say a proton travels at a speed of 5 times 10 to the 7 meters per second through a 1.0 Tesla magnetic field. What is the magnitude of the magnetic force of the proton if the angle between the proton's velocity and the magnetic field vector is 30 degrees? So now the angle, in this case, this is side number 33, the angle between the magnetic field vector and the velocity vector is 30 degrees. This angle is theta. So now theta here is 30 degrees. So when you apply the equation, it's the same equation. Force is equals charge of the, in this case, proton times the velocity times the field times the sine of the angle. So substituting the charge of the proton is the same as the charge of the electron, but positive. 1.60 times 10 to the negative 19 coulombs. Now the velocity or speed is just 5 times 10 to the 7 meters per second. The intensity of the field is 1 Tesla sine of 30 degrees. So when you calculate the force now here, it will give you 4.0 times 10 to a negative 12 newtons. 4.0 times 10 to a negative 12 newtons. So now, what is important to highlight in this case, when they say the magnitude of the magnetic force of the proton, find the magnitude of the magnetic force of the proton, if the angle between the proton's velocity and the magnetic field vector is 30 degrees. So theta is that angle. That angle is just zero. And it's just 30 degrees. Okay? Now let's see the other one. All these are basically different variations of the same type of exercise because it's just a charge that enters into a uniform magnetic field. Either an electron or a proton, you know, but it's a charge that enters into a magnetic field, right? At some angle, so perpendicular or at an angle, I don't know, 30 degree or 60 degree or whatever angle is that. Now look at this one. They say an electron moving perpendicular to a uniform magnetic field of 3.2 times 10 to the negative 2 Tesla is moving in a circular radius 0.40 centimeters. How fast is this electron moving? So in this case, what we have to do is to calculate the speed of the electron, right? But they give us the radius. Now remember that there is a relation when the electron is in a uniform magnetic field and the angle between the velocity of the electron and the magnetic field is 90 degrees, the electron is moving in a circular path, right? The electron is going to be moving in a circular path. Okay? Now, what happens? Then we can make the centripetal force, that is the force of the circular motion, equal to the magnetic force, right? So you have a magnetic force, and this magnetic force provides the centripetal force. This magnetic force is Q, the speed of the electron, intensity of the field. Now, sine of the angle will be 90 degrees. So it doesn't make sense in this case just to put the sine of the angle. They say it's perpendicular. So if perpendicular, theta is 90 degrees, and the sine of 90 degrees will be 1. If it's not 90 degrees, then it's going to be a helical path. It's not going to be a circular path, right? And then the centripetal force is mass times centripetal acceleration, and the centripetal acceleration is p squared over r, where p is the speed of the particle and r is the radius. Now what happens? You will simplify this b over here, this speed, with one of the speed of the p squared you have over here. So you will get that q times the intensity of the field is equal to mass times the speed over the radius of the circular path. So now when you solve for B, solving for B, what do you get? You get that Q, the charge of the electron, times the intensity of the field, times the radius of the circular path is equal to mass times the speed, and then Q, the intensity of the field, the radius, divided by the mass is equal to the intensity of the field. So the intensity of the field, equal to the speed. So the speed would be, what is going to be Q? The charge of the electron, which is 1.60 times 10 to the negative 19 coulombs. What is B? The intensity of the field. They said 3.2 times 10 to the negative 2 Tesla. What else? The radius, they say 0.40 centimeters. So 0.40 centimeters in meters would be 0.40 times 10 to a negative 2 meters. Divided by the mass. The mass of who? The mass of the electron is given also here. They say the mass of the electron is 9.11 times 10 to the negative 31 kilogram. And now you can calculate this speed, and when you calculate the speed, you will get that the speed is equal to 0.22 times 10 to the 8, which is at the end 2.2 times 10 to the 7 meters per second. 2.2 times 10 to the 7 meters per second. That would be the speed of the electron. So again here, well, you can really find this equation, right, of the radius. You can find this equation of the radius as part of the equation that we usually use. I show you here how we get the equation, making the magnetic force equal to the centripetal force. but this is one of the equations that is just, in your notes. Right? Now look at the next. They say an electron moving perpendicular to a uniform magnetic field of 0.22 Tesla move in a circle with a speed of 1.5 times 10 to the 7 meters per second. What is the radius of the circle? So now, from this same equation that we have, let's say that Q times the intensity of the field is equal mass times the speed divided by the radius. We have to solve for the radius. Because again, we have this electron moving perpendicular to a uniform magnetic field. So again, it's moving in a circular path because you have an electron, that enters the sun velocity perpendicular to the field into a region with a magnetic field. So the electron will be moving in a circular path, right? And then we want to find the radius of that circular path. So if you want to solve for the radius here, you can say that then Q B times R is equal to mass times the speed of the electron. So you can say that R is equal to mass, the speed of the electron divided by the charge of the electron times the intensity of the electron. So if you substitute, then R here would be the mass of the electron, that is 9.11 times 10 to the negative 31 kilograms times the speed of the electron, which is going to be 1.5 times 10 to the 7 meters per second. The charge Q, there is the charge of the electron, 1.60 times 10 to the negative 19 coulombs. The intensity of the field, there is 0.22 teslas. And when we find the value, we're going to get 38.8 times 10 to the negative 5 meters. Now they are giving this in millimeters, so we can say that this is the same that 0.39 times 10 to the negative 3 meters, which is 0.39 millimeters. And the answer key have an error here because the answer key shows 3.9 millimeters, but the right answer is really 0.39 millimeters. There's no way, I double check the calculation multiple times. There is no way that the answer would be just 3.9 millimeters. It needs to be 0.39 millimeters. Exercise number 36 is very, very similar. You know who is our exercise. So again, they say they have a charged particle of mass 0.0040 kilograms. It's subjected to a 4 Tesla magnetic field, which is acting at a right angle to its motion. If the particle moves in a circle of radius 0.10 meters at a speed of 2 meters per second, what is the magnitude of the charge of this particle? So it's the same equation again, but in this case, we want to solve for the charge. So now in this exercise, we have the same equation, the charge times the magnetic field equals to mass velocity over the radius. We want to solve for the charge. We can say that the charge is equal to mass velocity over the intensity of the field times the radius. Now, what is the mass here? The mass of the particle, 0.0040 kilograms. The speed, that is 2 meters per second. The intensity of the field, 24 teslas. And then finally, we have a radius, that is 0.10 meters. And then when you calculate the charge here, the charge will be 0.020 coulombs. 0.020 coulombs. That would be the charge in this case. That was the solution of the exercise number 36. So we have my answer here, it's answer C. Now, exercise number 33, 34, 32, I believe, let me double check. 32, 33, 34, and 35. All those exercises are basically about a particle that enters into a magnetic field, perpendicular or at some angle with the magnetic field, right? And then, this particle will follow a circular path. If it's perpendicular, it will follow a circular path. If it's not, then it will follow a helical path, right? And then we can just calculate different quantities based on that. Let's see now the next exercises are just about different things. These are about, a straight wire that is in a magnetic field. So let me erase, I can get some space here. Right, so let's see exercise number 37. In number 37, they say that there is a 2 meters straight wire carrying a current of 0.60 amperes, right? So we have a wire that carries a current of 0.60 amperes. Now, this is oriented parallel to a uniform magnetic field of 0.50 Tesla. So there is a uniform magnetic field here, like this. There is 0.50 Tesla. Right? Now, what happens? If we want to calculate the force there is acting on this wire, they say, what is the magnitude of the magnetic force on this wire? We know that the force would be equals to the current times the length of the wire times the intensity of the magnetic field times the sine of the angle, theta. That is the angle between the direction of the current and the field. What happens? Theta here is 0 degree, and the sine of 0 degree is C. So if we multiply by 0 all these other quantities, we will get that the force acting in this case will be 0. So when the current and the field have the same direction, the force there is 0. So the force acting on this wire as they are parallel, the current and the magnetic field are parallel, would be zero because the angle would be zero. Now, look at this order. Number 38 is very similar. You again have a wire with a current of 10 amperes. And then you have that the current have an angle of 30 degrees with respect to the direction of a uniform 0.30 Tesla magnetic field. So now the direction of the current and the direction of the magnetic field makes an angle of 30 degrees. So this is the magnetic field now. And there is an angle here of 30 degrees. So when we apply the same formula, say the force is equals I times L times B sine of theta. Then now theta is different of zero, so the force will be different of zero. So the force will be the current of 10 amperes times the length, that is 0.50 meters, times the intensity of the field, which is 0.30 Tesla, times the sine of 30 degrees. So the force would be, in this case, 0.75 newtons. 0.75 meters. Now, there, in this exercise number 38, they gave us the length of the wire. Because it was a wire, with length of 0.50 meters. Now, in the next exercise number 39, they don't know and they don't give us the length of the wire. So they say, what is the force per meter? When they say force per meter, they ask you for F over L. This is force per meter. Force per unit of length. Force per unit of length. Force per meter. So they say, what is the force per meter on a straight wire carrying 5 amperes when it's placed in the magnetic field of 0.020 Tesla, so that the wire makes an angle of 27 degrees with respect to the magnetic field lines? So we have the same equation, same formula. Force is equals current times length times the intensity of the field times the sine of the angle. But now it's just force per unit of length. So we don't know the length. We divide by L, we get force over L is equals to I E sine of zeta. So every time that they say force per meter, force per unit of length, what you have to do is find F over L, because the length of the wire is unknown. It's very long. So we have the current here, which is 5 amperes. We have the intensity of the field, that is 0.020 Tesla. And we have the angle, that is 27 degrees. So F over L would be, when we calculate that, in this case, 0.045 newtons per meter. This would be, in this case, the right answer. So the force per unit of length would be in units of force per unit of length, right? So newtons per meter. 0.045 newtons per meter. Let's discuss now the exercise number 40 here. We say a straight wire is carrying a current of 2 amperes. It's placed at an angle of 60 degrees with respect to a magnetic field of a strength 0.20 Tesla. If the wire experiences a force of 0.40 newtons, what is the length of the wire? So again, in this exercise 40 now, what we have a wire with a current of 2 amperes. And then with a field at an angle of 60 degrees of 0.20 Tesla. This angle is 60 degrees. So we have to calculate, in this case, the length. So we know that the force, we know that the force is equal to current times length times b sine of theta. If we solve for the length, we get that force over current intensity of the field sine of theta is equals to the length. So the length would be force, that is 0.40 newtons, divided by a current of 2 amperes a field of 0.20 Tesla. What else? An angle of 60 degrees. So now you can calculate the length. And when you calculate the length, you get 1.15 meters, which is approximately 1.2 meters. So what is going to be the length? The length of the wire under those conditions is going to be 1.2 meters. So you can see, always there are different variations of the same exercise, right? So different variations of the same exercise. So basically, we have the same equation where we can find for different quantities, right? We can solve for different quantities. In some cases for the force, in some cases for the length, in some cases for the charge. Let's see the exercise number 41. They say 2 long wires that are 30 meters, 0.30 meters apart carry currents of 5 amperes and 8 amperes in opposite directions. Well, now we know that the force will be repulsive, right? Because they are carrying currents, in opposite directions. So the forces will be repulsive. Find the magnitude of the force per unit of length that each wire exerts on the other wire and indicate if the force is attractive or repulsive. Always repulsive. Now, what we have? We have 2 wires here. One of them carrying a current of 5 amperes. And the other one carries a current of 8 amperes. Now, we know that the force, because we already did the analysis of this previously, will be repulsive. And well, the distance between the wires is 0.30 meters. Now, the force between two current carrying wires, we used that equation before, is mu sub 0 I sub 1 I sub 2 over 2 pi r. Mu sub 0 is a constant, 4 pi times 10 to the negative 7 Tesla, meters squared over ampere. Sorry, meters over Tesla, meters over ampere. We know I1 and I2, and we know the distance, so we can calculate the force. So the force will be here 4 pi times 10 to the negative 7 Tesla meters per ampere times 5.0 amperes times 8.0 amperes all over 2 pi times 0.30 meters. So now we can calculate the force, and that force will be approximately 2.7 times 10 to the negative 5 newtons. And it's a force of repulsion. It's repulsive. It's a repulsive force. So we know repulsive because we did analysis before, in one of the first exercises, right? Any question? So my recommendation is when you be doing the calculations, right? Well, if your calculator let you do it, just put everything, including 10 to the negative 7, 10 to the blah, blah, only the calculator as a fraction, Or if not, work with all these other decimal numbers or integers, right? And at the end, just combine the powers of 10. So leave alone the powers of 10, so you can work with the powers of 10 at the end. If not, it would be very confusing. So now, let's see the next set of exercises about circular coils, including torque. So there are some problems, a couple of problems at least about torque here, 42 and 43. So let's see those exercises. So in exercise number 42, they say that a flat circular coil have 200 identical loops of very thin wire. Each loop has an area of 0.12 meters squared and carries 0.50 amperes of current. This coil is placed in a magnetic field of 0.050 Tesla oriented at 30 degrees with respect to the plane of the loop. What is the magnitude of the torque on the coil? So, well, we have a loop, a circular coil, they have 200 turns or 200 loops. And this is the area, the inner area of this circular coil, right? Which is 0.12 meters squared. And we do know that there are 200 terms, right? Now, we know that there is a magnetic field, but now let's see one side view of this. So this is my coil in a side view. So what I see when you look from this side to this coil, you will see basically like only one thin wire. So this here would be the normal to the plane of the coil, and that is important when we have coils and we have areas. The angles are measured with respect to that normal. And then we have the field, and this field, is at an angle of 30 degrees with respect to the plane of the loop. So there is a magnetic field here. But this magnetic field is at 30 degrees with respect to the plane of the loop. So 30 degrees here. Now, the torque equation to calculate torque would be the number of turns times the intensity of the current times the area times the intensity of the field times the sine of the angle theta. Now, who is this angle theta? This angle theta is not 30 degrees, because 30 degrees is the angle between the field and the plane of the coil, and theta is the angle between the field and the normal to the plane of the coil. So I'm going to do something. We know that the field have multiple lines there, right? But I will just leave only one line representing the field. Well, theta would be this angle. Is the angle between the normal to the plane of the coil and the intensity of the field. So theta here would be 60 degrees. So now when they say what is the magnitude of the magnetic torque of that coil, that torque would be 200 turns times the current, there is 0.50 amperes, times the area, there is 0.12 meters squared, times the intensity of the field, that is 0.050 Tesla, times the sine of the angle, that would be 60 degrees. So when you calculate torque, with all these values, you will have that the torque would be 0.52 newtons meter. So the torque would be 0.52 newtons meter. Sorry. This would be the torque in this case. So let's keep working, in the solution of this exercise. Let's try to solve as many exercises as possible, right? So let's now go over the exercise number 43. And in this exercise number 43, they say that a flat circular loop of wire is in a uniform magnetic field of 0.3 Tesla. The diameter of the loop is 1 meter, and a 2 amperes current flows in it. What is the magnitude of the magnetic field torque on the loop when the plane of the loop is parallel to the magnetic field? When the plane of the loop is parallel to the magnetic field. Well, Sorry. What we know the intensity of the field, which is 0.30 Tesla. We know the diameter of the loop, which is 1 meter. And we know the current that flows through this loop, there is 2 amperes. What else we know? We know that the plane of the loop is parallel to the magnetic field. So the loop is just a circular loop. If the plane of the loop is parallel to the magnetic field, so let's say that the current flows through this loop in this way, this is the current, then we have the magnetic field will be like this. So the magnetic field is parallel to the plane of the loop. You know? So if you make a side view of this, you will see the loop here. For example, if I look at this from below, and I will see the magnetic field. Sorry, let me just put the magnetic field group. We see the magnetic field like this. Now, really remember that what matters is the angle between the normal to the plane of the loop and the magnetic field. So the normal to the plane of the loop is this vector. And the angle, theta, between the normal and the magnetic field is 90 degrees. So the angle between the normal and the magnetic field is 90. So that means that when they say what is the magnitude of the magnetic torque, well, we know the torque is equal to the number of turns times the current times the area times, the intensity of the field and the sine of the angle theta. Now, in this case, we have only one loop, right? So n is 1. The area will be pi d squared over 4. So it would be pi times 1.0 meters squared over 4. So the area would be pi over 4 meters squared. So I can calculate the torque, which is 1 times the current, that is 2 amperes, times the area, that is pi over 4 meters squared, times the intensity of the magnetic field, which is 0.30 teslas, times the sine of the angle, which is 90 degrees. So when you calculate the torque, this torque here would be 0.47 newtons meter. 0.47 newtons meter. So exercise 42 and 43 were both about torque. And again, I want to emphasize, right, first, the equation to calculate the torque. You have a coil. And in addition to that, to emphasize, right, that the angle theta that we see here in the equation of torque is the angle between the magnetic field and the normal to the plane of the loop. Between the magnetic field and the normal line to the plane of the loop. So don't get confused. Remember that the angle, in the case of the coils, right, is not measured with respect to the plane of the coil, it's measured with respect to the normal to that plane of the coil. So if the plane of the coil and the field are parallel, then the angle is 90 degrees because the normal is perpendicular to the plane of the coil. Now, exercise 44 and 45 are exercises about, in this case, the intensity of the magnetic field surrounding a carrying current wire. Look at this exercise. They say a high power line carries the current of 1 kiloampere. What is the strength of the magnetic field this line produces at the ground, which is 10 meters away? You have a wire here, you have the ground, and you have that this wire is 10 meters above the ground. Now, we want to know what is the intensity, the strength of the magnetic field at the ground, which is 10 meters away from this wire. Now, this wire, we have a current of 1 kiloampere. Remember the prefixes. Kiloampere is going to be 1,000 amperes, right? Or 1 times 10 to the third amperes, right? So they want to find what is the intensity of the field here at this point on the surface of the ground due to this wire. Now, how we can calculate that? The magnetic field surrounding a current carrying wire is equal to mu sub 0 times I and the current over 2 pi r. Mu sub 0 I over 2 pi r. This is how you calculate the magnetic field, surrounding a current carrying wire. So you can see, with the increase of the distance from the wire to the point where you want to calculate the magnetic field, there is a decrease in the intensity of the magnetic field. So as closer you are to the wire, the stronger the magnetic field, of course. Now, in this case, mu sub 0, 4 pi times 10 to a negative 7 Tesla meters per ampere, a current of 1,000 amperes divided by 2 pi times 10 meters. So when you calculate this, you will find that the intensity, the strength of the magnetic field would be 20.0 times 10 to a negative 6 Tesla, which is the same that 20.0 micro Teslas. So 20 micro Tesla. For the exam, please try to, be familiar with your calculator. Try to remember how to use your calculator, every single function, because part of the success will be on how good you can do the calculation. The formulas are not really difficult. The problems are just very straight problems, that just ask you for something without, being too sophisticated. But it's important that you be able to identify the evens, the nums, and then later use the calculator, in a correct way. Now look at the next one, number 45. It's pretty similar to this one. But in this case, it's going to be the same formula, right? Basically. But ask you for a different quantity. Because they say how much current must flow through a long straight wire for a magnetic field strength to be 1 millitesla at 1 centimeter from the wire. So it's exactly like the previous problem, 44. In 44, you were asked to calculate the magnetic field at a given distance. In this other, you are asked to find the current, for a given magnetic field at a given distance. So again, they say how much current. So in 45, we have the wire, and we have some current flowing to this wire, right? And then we're going to have, of course, a magnetic field surrounding this wire. And then we want to know what is the current, if we have that at 1 centimeter, so at one point here, that is at 1 centimeter from the wire, the strength of the magnetic field is, in this case, 1 millitesla, 1.0 millitesla. The m lowercase is milli, right? So what we have to do here is find I. I is the unknown. So we know that the intensity of the field would be u sub 0 I over 2 pi r. If I have to find I we say that 2 pi Vr over mu sub 0 is equals to I. So before I, so you multiply by 2 pi r both sides and divide by mu sub 0. So you can say that the current is 2 pi times 1 millitesla is 1.0 times 10 to a negative 3 Tesla. 1 centimeter in meters is 1.0 times 10 to a negative 2 meters. So remember, always convert the centimeters to meters. Millitesla, so microtesla to Tesla. Milliamperes, microamperes to amperes. Right? And then mu sub 0, that is the constant, that is 4 pi times 10 to the negative 7 Tesla meters per ampere. So when you calculate the current, we get the current here is 0.5 times 10 to the second amperes, which is the same as 50 amperes. So in this case, the current is 50 amperes. Now, exercise number 46 is probably the most challenging exercise we have here. But it's because of, it's an exercise again involving 3D, involving uh, to work in the space in 3 dimensions, right? That makes the exercise difficult to understand. But when you understand it, it should not really be too difficult. So let me show you this exercise number 46. What they say in this exercise number 46. They say a circular metal loop of radius 10 centimeters and 3 long straight wires carry currents of ISO1, which is the current to the wire 1. ISO1 is the current in the loop. This is ISO1. Look at this. Is this current here in this loop is equal to 60 amperes. I sub 2 is the current in this straight wire. Is a current of 20 amperes. So this one is 60 amperes. This one is 20 amperes. Now, I sub 3 is the current in this wire. But this is a wire that is leaving the plane. It's coming from the plane, it's perpendicular to the plane. That wire is perpendicular to the plane. So what you see is like a little circle. And when you see this dot over here, is because the current is coming in this direction. So I sub 3 is 70 amperes. And then I sub 4, look at this. What you see is a circle, because you see the section of the wire. And when they show you the cross, it's because the current enters into the plane of the current enters into the plane of the paper, the plane of the computer. And ISO 4 is 30 amperes. Now, they say each of the straight wires is 20 centimeters from the center of the loop. The axes are shown in the figure below, with the positive 6-axis coming out of the paper. What is the Z component of the resultant magnetic field at the center of this loop? What is the Z component of the resultant magnetic field at the center of the loop? Well, look at this. The magnetic field due to I3 is a magnetic field that will be surrounding this wire and will be counterclockwise wires. So this is B3. So these magnetic field lines, right, that are just like circular, surrounding the wire 3 with current I sub 3. This magnetic field is parallel to the plane. Is parallel to the plane of the loop. So it doesn't affect the magnetic flux, right? And it doesn't generate any component of magnetic field in the Z-axis. So it doesn't create doesn't create a component, of magnetic field in z-axis. Why? Because the z-axis is the axis leaving the plane, and that magnetic field is acting in this way. Now, this over here is the same story. The magnetic field will be surrounding this wire, concentric to the wire, and then in this case, the direction of this magnetic field will be clockwise. Okay, this is before, and again, as this magnetic field is in the same plane, right? That is loop, it doesn't create any Z component of magnetic field, so exactly as the wire tree. So this one doesn't create a component of V on the Z-axis. So we can forget about both. So what basically we have, what we really have here that can create components, right, on the Z-axis are the loop and the wire that we have here below going from left to right. So these are the two wires that can create a Z component of the magnetic field. So in this one, we have a current I sub 1 equals to 60 amperes. And then in this one, I will use a different color to differentiate also later. The magnetic fields, we have a current I sub 2 of 20 amperes. Now, how is the magnetic field? Look at how is the direction of the magnetic field, due to the current I2. If you use the right-hand rule and you put your thumb in the direction of the current I2 and you wrap your fingers around that wire, you see how the magnetic field is leaving the plane above the wire and it enters into the plane below the wire. And it's going to be in the same direction that the positive z-axis. Right? It will be in the same direction of the positive z-axis, because the positive z-axis is leaving the plane. So the z-axis is like this. Now the current I sub 1 creates a magnetic field that in the inner part of the loop goes into the plane of the paper, and outside the plane of the loop goes out of the plane of the paper. So the magnetic field due to the red current would be like this. Inside like this, and outside is like this. So they say, what is the Z component of the resultant magnetic field at the center of the loop? at the center of the loop. So inside the loop, at the center of the loop. So that magnetic field, the resultant magnetic field at the center of the loop, will be equal to the magnetic field due to the current 2 minus the magnetic field due to the current 1. Well, if it's a vector sum, we can just add these vectors, but we know that these vectors have different directions. So I can just represent an addition of 2 vectors, but these 2 vectors have opposite directions. So later, I will get just V2 minus V1. So V resultant will be really V2 minus V1. Now, V2 is the magnetic field due to a straight wire. The magnetic field due to a straight wire is mu sub 0 I sub 2 over 2 pi R2. This is the magnetic field at the center of the wire, because we know that the distance from the center, the loop, sorry, from the center of the loop to this wire, this distance is 20 centimeters. Now, the magnetic field due to V1, due to the current 1, magnetic field V1 due to the current 1, is the magnetic field due to a circular loop. And then the equation is a little bit different. So the equation is mu sub 0 I sub 1 over 2R1. So there is no pi in that equation. There is no pi in that equation. That means that now if I want to find the resultant in the z-axis, this resultant in the z-axis will be mu sub 0 I2 over 2 pi r sub 2 minus mu sub 0 I sub 1 over 2 r sub 1. We can take a common factor mu sub 0, we can take a common factor mu sub 0 over 2 out. We say mu sub 0 over 2 times I sub 2 over pi r2 minus I sub 1 over r sub 1. So you want to calculate this now. Say what is mu sub 0? 4 pi times 10 to the negative 7 Tesla meters per ampere over 2 times the current 1 is, sorry, the current 2 first is 20 amperes over pi times r sub 2, that is this distance, 20 centimeters. 20 centimeters is 0.2 meters. Minus, now the current of 60 amperes, I sub 1 divided by R1. R1 is the radius of the loop, and the radius of the loop was just 10 centimeters. So 10 centimeters is 0.10 meters. So when you now calculate that, you will find that this will be negative 356.9 times 10 to the negative 6 Tesla, which is the same as negative 360 microtesla. What is the meaning of the negative sign? The meaning of the negative sign here is, of course, that the field that enters into the plane that goes against the direction of the z-axis is larger than the field that goes in the direction of the z-axis. So that's why it's negative, because the resultant field points toward the plane. It points toward the plane. That's why we get a negative sign. But the key in this exercise is to recognize, right, that these current I3 and I4, have a magnetic field that are in the same plane that the plane of this loop, so they cannot create a Z component of magnetic field. So the only possible Z component of magnetic field is due to the straight wire that you see here below and the loop. And the formulas are different. So the field due to the straight wire is this one. This is the equation for field, magnetic field due to a straight wire. And this so is the formula for the magnetic field at the center of a loop. So when we combine both together, we can calculate the Z component of the magnetic field. This one is probably the most difficult exercise that is in this review. Let's now solve some problems about solenoids. Let's solve some problems about solenoids and eventually, inductance. So let me erase that, what I did over here. So I get a space, to solve those other exercises. Remember, the exam is open notes. So make sure to take notes of all the videos that we did in classes here, right? Because it's gonna help you a lot. You have good notes to solve the exam. Now look at the next problem here. They say an ideal solenoid, this is exercise number 47. An ideal solenoid is 34 centimeters long and is carrying a current of 2 amperes. If the magnitude of the magnetic field generated at the center of the solenoid is 3 millitesla, how many turns of wire does this solenoid contain? So remember that a solenoid is just a wire that has been wrapped in this form. These have a number of terms, which is n, which is the unknown. It has a length. There is this. That they say that the length of the solenoid is 34 centimeters, which is 0.34 meters. They say that it carries a current you know, of 2 amperes. So if it carries a current of 2 amperes, imagine, that we have a current that goes like this. Sorry. And then if this current, flows in this solenoid in this direction, just going like this, right? Then the magnetic field induced in the solenoid will be here. This will be the magnetic field. And this magnetic field is 9 milliteslas, right? This magnetic field is inside the loops, pass through inside the loops, right? So we want to find how many terms are here. So this magnetic field in a solenoid can be calculated like mu sub 0 n over L times I. Mu sub 0 times n over L times I. Where I is the current and the number of terms, L is the length, mu sub 0 is the constant, B is the field in the inner part of the solenoid, the center of the solenoid. So if we solve for n, we get that B times length, the strength of the field times the length, is mu sub 0 times the number of terms times the current. Solving for the number of terms, we said BL over mu sub 0 I is equal to the number of terms. So the number of terms of this solenoid is 9 milliteslas is 9.00 times 10 to the negative 3 Tesla. The length 0.34 meters over mu sub 0 4 pi times 10 to the negative 7 Tesla meters per ampere times the current, that is 2 amperes. So n would be, when you calculate that number of terms using this equation that I show you, this number of terms would be 1,218 terms approximately, which is approximately 1,220 terms. So how many terms have the solenoid? You have 1,220 terms. Now, the next exercise 48 is very, very similar. Because again, in 48, you have solenoid. I don't want to solve it. I just will give you the tips to solve 48 and 49. So you have, in this case, in 48, you have your solenoid, and you want to calculate how much current is passing through this solenoid. You have that n is 400 terms. The solenoid have a length of 4.0 centimeters, which is 4.0 times 10 to the negative 2 meters. It have a magnetic field at the center of the solenoid of 1 Tesla. So you have just to calculate in this case how much current. So you know that B is equals mu sub 0 n over L, n over L times I. You want to calculate the current I, you multiply B times L over mu sub 0 times N. This will be I. So you can substitute in this formula, and like that you can calculate, in this case, what is the current. If you calculate the current, this current should be approximately 80 amperes. Now 49, again, is another variation of this same problem, using exactly, the same formula. In this case, again, they want to find the number of terms. So it would be basically like this one, like 47. So 49 and 47 are similar exercises, where they give you the length, they give you the intensity of the field, they give you the current, and they ask you for how many terms. So what equation will you use? You will use the same equation that we have using number 47. So in number 49, you use the same equation that in 47 to calculate the number of terms. And they give you everything. So the field 1.5 millitesla, the length 10 centimeters, the current 1 ampere. We know the constant mu sub 0, so it's just to find the number of terms. So it's exactly the same thing. Now, let's see then the next exercises, 50, 51, discussing about magnetic flux. So I will erase, this part here to get some free space work. So in exercise 50, they say that they have a flat circular loop, of radius 0.10 meters. This is in a uniform magnetic field of 0.20 Tesla. So they want to find, what is going to be the magnetic flux to the loop when the plane of the loop and the magnetic field vector are parallel. So you have your loop, this is the plane of the loop, and now the magnetic field vector is parallel to this plane of the loop. Now, what we know about magnetic flux? We know that the magnetic flux would be basically a measure of the number of magnetic field lines that pass through an area. So if the plane of the loop and the magnetic field vector are parallel, the number of magnetic field lines passing through the plane of the loop is 0. So the magnetic flux here needs to be 0. Also, think about this. You know that the angle theta to calculate magnetic flux, and the equation for magnetic flux is VA cosinus theta. The normal to the plane of the loop, if the plane of the loop and the magnetic field are parallels, the normal to the plane of the loop makes an angle of 90 degrees with the magnetic field. And the cosine of 90 degrees is 0. So this also, theta is 90 degrees. The cosine of 90 degrees is going to be 0. So again, the magnetic flux will be 0. But it's common sense. If the magnetic field lines are parallel to this plane, there are no magnetic field lines crossing to the plane of the loop. And magnetic flux is a measure of the magnetic field that goes to that plane, to the area of the plane. So in that case, the magnetic flux is 0. Now, they changed later the problem, and in 51, they say, oh, a flat circular loop of 0.10 meters of radius is rotating in a uniform magnetic field. So now this loop is rotating in this magnetic field. So you have, the same radius of 0.10 meters. And then there is the same magnetic field of 0.20 Tesla. Now, but this is now rotating. Find the magnetic flux to the loop when the plane of the loop and the magnetic field vector are perpendicular. When the magnetic field vector, and the plane of the loop are perpendicular. So when they are perpendicular, that means that the magnetic field vector is either leaving the plane or entering into the plane of the loop, right? Depending on, they didn't specify any direction for the magnetic field, but we know that it's going to be something like this. So now, when you analyze the side view of this, here you have the loop, here you have the normal, and now here you have the magnetic field. The angle between the magnetic field and the normal is 0 degree. So theta is 0 degree, and the cosine of 0 degree is 1. So we get a maximum flux, the maximum magnetic flux. So this magnetic flux maximum will be VA, and will be then the intensity of the magnetic field, which is 0.20 Tesla, times the area, that is pi times the square of the radius, so 0.10 meters squared. So the intensity of the magnetic flux here will be, when you multiply that, 6.3 times 10 to a negative 3 Tesla meters squared. So remember always this, when you're calculating magnetic flux, if the plane of the loop is perpendicular to the magnetic field lines, your magnetic flux should be 0. If the plane of the loop is, if the plane of the loop and the magnetic field lines are parallel, the magnetic flux is 0. If the magnetic field lines and the plane of the loop are perpendicular, then in this case, the magnetic flux is maximum, and it's equal to VA. It's equal to the intensity of the field times A, which is the angle in this case will be 90 degrees, and will be cosine of 90 will be 1. Now, the next exercise are about coils again. but we have a change in magnetic flux. So there will be an induce of electromotive force, be an induction of electromotive force. So let me explain now exercise number 52. Look at this one, 52. They say that you have a circular coil with 20 turns. So n is equal to 20 turns. And this circular coil have a radius of 5.0 centimeters, which is 5.0 times 10 to the negative 2 meters. This is the radius of the circular coil. Now, what else? They say that is placed with its plane oriented at 90 degrees to a uniform magnetic field of 0.10 Tesla. So the magnetic field is 0.10 Tesla, is perpendicular to the plane of the loop So that means that the angle theta is 0 degree, and the cosine of 0 degree will be 1. So we will have the maximum magnetic flux. Now, what did they say? The field is now increasing at a steady state, reaching a value of 0.50 Tesla after 4 seconds. So now, this was the initial field strength, but there will be an increase in the field strength. So the field strength will go from 0.10 Tesla to 0.50 Tesla. And it will take a time of 4 seconds to reach that value. So they are asking about what is the induced electromotive force in this coil. So we want to know what is the induced electromotive force in this coil. Now, what is induced electromotive force? Due to a change in magnetic field. The induced electromotive force due to a change in magnetic field is equal to negative the number of terms times delta phi sub b over delta t. So the negative. Why the negative? Because remember that this electromotive force that will be induced will oppose to whatever change occurs, right? That is the reason of the induce. So if there was an increase in the intensity of the field from 0.10 Tesla to 0.50 Tesla, you know, the electromotive force that will be induced as a later. You know, there will be a magnetic field that will oppose to that increase, right? That's the reason of the negative sign. Okay, so that's why you don't see later any answer here negative. Regardless that I will keep the negative sign and we work with the negative sign, the answers are positive because the negative sign has only one meaning. It opposes to the change, to whatever change have occurred, right? So now, what happened with delta phi b? Well, in this case, the electromotive force would be negative n times phi sub b final minus phi sub b initial. So the final magnetic flux divided by the initial magnetic flux divided by the variation of time, or the time that it takes for this variation. Now, what is this final magnetic flux? Will be BA, B final times A, by the area. It's minus N times the B final times the area minus the initial magnetic flux is B initial times the area. I am just multiplying just B final times the area, B initial times the area, because I said, you know, that the plane and the magnetic field are perpendicular, so the angle is 0 degree, so the cosine of 0 is 1. So we have the maximum magnetic field value, that is VA. So that's why I don't use cosine of theta. I don't say VA cosine of theta because cosine of theta will be 1 because it's cosine of 0 degree. So now the area is the same. So we can say that the electromotive force is equal to minus n times the area. It's not changing. So B final minus B initial over delta T. Now we have 20 terms. So it's minus 20 times B final 0.50 Tesla. B initial 0.10 Tesla. Divided by the time that it takes, that this chain takes is just 4 seconds. So when we calculate the electromotive force that was induced, we get that this induced electromotive force would be, oh, I forgot to include the area here, sorry. I didn't include the area. So the area, we know the radius, so the area would be pi times r squared. So it's pi times, what is r? 5.0 times 10 to the negative 2 meters squared, and then 0.50 Tesla minus 0.10 Tesla. This is the area. Pi times 5.0 times 10 to the negative 2 meters squared. It's on the square here for the meters. Now, when we calculate this electromotive force, it would be minus 157 times 10 to the negative 4 volts. So it would be minus 0.016, So now moving the decimal point 4 places to the left, minus 0.016 volts. So I can just go and pick positive 0.016 volts, because remember that the minus is only because this induced electromotive force opposed to the change, whatever change have occurred. In this case, the change was that there was an increase in the intensity or the strength of the magnetic field. We have only 4 more problems to solve. Problem 53, I will say that is the second more difficult problem. Problem 53, I will say the second more difficult problem. The one that had all those wires, and you have to find a component in the z direction of the magnetic field. I would say that was the most difficult. And now the second most difficult problem to me is this number 53. Let's see why. In this problem number 53, they say, shown below, a wire and a 10-ohm resistor are used to form a circuit in the shape of a square with dimensions 20 centimeters by 20 centimeters. A uniform but non-static magnetic field is directed into the plane of the circuit. So the magnetic field is uniform, but it's changing with the time. So the magnitude of the magnetic field is decreasing from 2.70 Tesla to 0.90 Tesla in a time interval of 96 milliseconds. What is the induced current in the circuit, and what is the direction to the resistor? Well, the current that will be induced will be equal to the electromotive force that is being induced divided by the resistance of this resistor we see over here. So now we have to do a similar process to exercise number 52 to calculate this electromotive force induced. So this electromotive force that is being induced, we know that is minus n delta phi sub t over delta t. We know, right, that in this case, again, the magnetic field is perpendicular to the plane, of this square, of this circuit with the shape of a square. So the angle theta, between the normal to the plane and this magnetic field is 0 degree, and the cosine of 0 degree is going to be 1. So I can get rid, I know that, delta phi b is BA cosine of theta, but since this will be 1, because theta is equal to 0 degree, this will be just BA. Now, we know that B is changing, so the electromotive force is equal to negative the number of turns times phi B final minus phi sub B initial over delta T. So this electromotive force will be the number of turns, which is 1 in this case, because it's just only a circuit. Now times phi B final is B final times the area minus B initial times the area. Phi sub B initial over delta T. We know this area is 20 centimeters by 20 centimeters, so it's 0.2 meters, because 20 centimeters is equal to 0.2 meters times 0.2 meters, which is 0.04 meters, which is 4.0 times 10 to the negative 2 meters squared. So meters squared. So this electromotive force that is being induced will be negative. Then we have common factor area and delta T, and then we have B final minus B initial. So it will be negative 4.0 times 10 to the negative 2 meters squared. Delta T is 96 milliseconds. So it's 96 times 10 to the negative 3 seconds, because milli is 10 to the negative 3. And then B final minus B initial, B final minus B initial. So we have a decrease. B final is 0.90 Tesla minus B initial, which is 2.70 Tesla. So at the end, we're going to get here that this is 0.75 volts. So this is approximately, 0.00075 times 10 to the third volts, which is 0.75 volts. This would be the electromotive force induced. So now to calculate the induced current, you divide the 0.75 volts by the 10 ohms that have this resistor, it gives you 0.075 volts. It gives you 0.075 volts. The answer is here. Sorry, oh no, amperes. Sorry. So the answer is here at in milliamperes. So you will say that this is 0.075 times 10 to the third milliamperes per ampere. So it would be basically 75 milliamperes. It would be 75 milliamperes. So the answer is 75 milliamperes. Now, what is the direction of the current? Well, what is going on here? We have a decreasing, right, magnetic field. So the magnetic flux through this square is decreasing. So the current that is being induced must counteract that decrease. And it must counteract the decrease. It must point in the same direction that the magnetic field we actually have. So the magnetic field induced by the current that will be induced will be also pointing toward the plane, entering into the plane. And the only way you know that in the inner region of that circuit, you have a magnetic field that enters into the plane is if the current flows from B to A, is if the current flows in this direction. So with a current flowing in this direction in the circuit, you will get, you know, the magnetic field that enters into the plane. Just do the right-hand rule. So just put the thumb in the direction of the current and now wrap your fingers around the wire. Just, for example, take the bottom part, and when you wrap the fingers around the wire, you know, you see how your 4 fingers enters above the wire into the plane and are leaving the plane below. So that's why you have that this is from B to A. So the right answer here is 75 milliamperes from B to A. Now, the last 3 problems are about inductance. I will explain 2 of them. The 54 and the 55. So what is the problem number 54? They say, what is the self-inductance? Self-inductance is L. Now, remember that when you have a solenoid, right, instead of, you have a resistor, you have resistance. When you have a capacitor, you know, we have the capacitance, which is what characterizes a capacitor. When you have an inductor, what characterizes an inductor is the inductance. You know, and that inductance is just defined by the letter L. So we have that L is just what we want to calculate, this self-inductance. This self-inductance, exactly the capacitance, depends on the geometry of the capacitor. The inductance depends, you know, on the geometry of the inductor. Exactly the capacitance depends on the geometry of the capacitors. Remember the capacitors with all those area, distance between plates, you know, direct constant. Now the inductance is placed on the geometry. So they say that what is the self-inductance of an ideal solenoid that have 30 centimeters long? So the length is 300 centimeters, which is going to be 3.0 meters, with a cross-sectional area, so they give you the area, of 1.00 times 10 to the negative 4 meters squared, and it has 1,000 terms. 1,000 terms. Now, what is the equation to calculate the inductance? The inductance is equal to mu sub 0, a constant mu sub 0, the square of the number of terms times the area over the length. That is the equation to calculate the inductance of an inductor. So this is the length. And the area, of course, will be the area of the terms. So here we're going to have some area. Right? So we can now calculate inductance. 4 pi times 10 to the 7, 10 to the negative 7, sorry. Tesla meters per ampere times the number of terms is 1,000 squared times the area, which is 1.00 times 10 to the negative 4 meters squared. Sorry, meters squared here. Divided by the length, and the length is just 3 meters. So the inductance of this inductor, when you just do those numbers, you get 4.19 times 10 to the negative 5 Henry. 4.19 times 10 to the negative 5 Henry. Now, they are expressing the answers in milli, nano, micro, pico Henrys. So I can just move the decimal point one place to the right, get 41.9 times 10 to the negative 6 Henry. So it would be 41.9 micro Henry. 10 to the negative 6 is micro. So this will be 41.9 micro Henry. 41.9 microhenry is answer B. Now, the exercise 55 and 56 are very, very similar. They both use the same equation. That is the equation that let us calculate the electromotive force in a circuit that contains an inductor, right? If there is a change in the current that flows to the circuit as a function of the time. So in exercise 55, they say that we have a coil with a self-inductance of 6 Henry. So L is 6 Henrys, 6.0 Henrys. What else? It's connected to a DC battery to a switch. As soon as the switch is closed, the rate of change of the current is 2 amperes per second. Rate of change of current in amperes per second. This is delta I over delta T. Delta I over delta T gives you the rate of change of the current with the time. And this is 2.0 amperes per second. They ask you now what is the electromotive force. Well, for inductors or circuits with inductors, electromotive force would be minus L delta I over delta T. So again, minus L, because it means, that this induced electromotive force will oppose to the changes, right, in the magnetic field due to the inductor, and due to the variation of the current with respect to the time to the, then the magnetic field to the inductor. So this electromotive force would be minus, what is L? 6 henries. What is delta I over delta T? 2 amperes per second. So this electromotive force would be minus 12.0 volts. Minus 12.0 volts. And then the exercise number 56 is very similar. So it's basically the same.